Hey everyone, in this lesson, we're going to use our understanding of limits to dive into the definition of derivative. My hope for you is that you gain a solid understanding of what a derivative really is. I want you to see how powerful a tool a derivative can be to describe real change in the world around us. Things like motion, speed, decay, growth, anything that changes over time. It's been my experience, both as a student and as a teacher, that a strong conceptual understanding of the definition of derivative is key to a firm foundation that opens the door to being able to acquire and apply skills in differential calculus. In my 30 plus years of teaching calculus, nearly all of my students become experts in derivatives. Some had to work a little harder than others, but ultimately they were successful, and I'm confident that you will be too. So let's get started. To develop this concept, let's take a look at a familiar distance versus time graph from our algebra background. Now let's plot a point on this graph, and this point represents at a given time a certain location. So in this scenario, at negative 10 seconds, we are located at, it looks like maybe 5 meters. Okay, so this location here would be like negative 10, 5. Okay, so if we set this in motion, you can see that as time goes by, the distance is changing. And not only changing, but it's increasing. Okay, so let's take that point and move it back to a time of 0. Okay, so what I'm going to do here, we're going to call that our initial point, and we're just going to go ahead and move this ahead 10 seconds. And I'm going to keep track of my initial point and my final point. Now what I'd like to do is I'd like to write the ordered pairs for each one of those points. My initial point looks like maybe 0, 20, and my final point here would be, let's say 10, 50. Now what I'd like to do is I would like to connect those 2 points with a line. Now we call that a secant line. A secant line is a line that intersects a curve at exactly 2 points. Okay, so now with this secant line, I'm going to calculate the slope. Okay, so let's do that. So my slope is rise. In this case, it would be 50 subtract 20 over run, which would be 10 subtract 0. Let's simplify that. I would have 30 on top. I would have 10 on bottom. Further simplification leaves us with 3 over 1. Okay, so what does this mean? Well, notice from our initial position to our final position, we covered a total distance of 30 meters. Okay, right here. And we did that in a total time of 10 seconds. And when we simplify that, we have 3 over 1. Now, what is that? Well, if we label that, okay, the top label, our rise label, is meters, and our run is seconds. So you can see that this slope of this secant line represents a rate of change, 3 meters per second. It's the average rate of change, okay? Because initially, here we were, and our final position was there, and this is the overall rate of change. We call that our average rate of change, okay? So the slope of a secant line represents the average rate of change. Okay, so we have 3 meters per second. Let's go ahead, take a look at our next 10 seconds. So our initial position would be at 10, 50, and our final position would be at 20, 125. So again, we're going to connect these 2 points with a secant line. Now let's calculate the slope this time. All right, so our rise would be 125, subtract 50, and over run would be 20 minus 10. If I simplify that, we have 75 on top of 10, and let's go ahead and write that as 7.5 over 1, a unit rate. Okay, and now if we place our labels this time, we have meters on top, and we have seconds on bottom. Okay, so in this time, our average rate of change is 7.5 meters per second. Okay, well, if you compare this slope with this one, you can see that the slope is steeper, so it kind of makes sense. We're covering more ground, so we need to move faster. Okay, so let's take a look at one more scenario. Okay, so this time we're going to place our initial at 20, 125, and our final up here, we'll call that 30, 325. Okay, so we're going to connect those with a secant line. Now, let's calculate the slope. All right, so we have rise, 325, subtract 125, over 30, subtract 20. On top, we have 200. On bottom, we have 10. Simplifies to 20 over 1. Let's label that. The top label is meters, and the bottom label is seconds. So in the next 10 seconds, from 20 to 30, you can see that the average rate of change is 20 meters per second. What if I'm not that interested in average rate of change? What if I'm more interested in instantaneous rate of change? That is, the rate of change at a given moment in time. Okay, so let's represent a location in time, just one location in time. And I want to know what the rate of change is at that point, at that instant. Okay? So again, we can do this with a line. Let me go ahead and sketch a line in here. Now that line is called a tangent line. It's called a tangent line because the word tangent means touch. And this line only touches the curve at one single point. So that's called a tangent line. Now again, I can move that point along the curve. I can, as time goes by, you'll see that that point changes. Notice what happens to the steepness of the tangent line. The slope increases as it moves along, representing an increasing rate of change. Now, let's leave this familiar distance time graph and go to something a little more generic. Okay, so notice that we have the same curve, but I don't have my axis labeled. I don't have my x-axis or my y-axis labeled. Let's look at a single point on our graph. Since we have no labels along the x-axis or the y-axis, we need to come up with a plan to label our point. So from the origin, we're going to say we move over some distance x along the x-axis. Likewise, we move up some distance f of x along the y-axis. Okay, so now we can label that point from the origin x comma f of x. Now this is variable. What that does is it allows us to move that point anywhere along the curve. So x comma f of x can be anywhere. Now, we want to find the instantaneous rate of change at that point. And remember, we can represent that with a tangent line. And again, because that point is variable, this tangent line can be anywhere along our curve. Okay, so let's just go ahead and place it right there. Because we need 2 points to calculate the slope of a line, I'm going to go ahead and place another point on the curve. Okay, so we need to come up with an ordered pair for this point. Okay, notice that the point that I placed on the curve is some random distance away from the original point. So along the x-axis, we're going to label that distance with an h. So from our first point to our second point along the x-axis, I'm going to label that with an h. Okay, so from the origin, remember that our first point is located a distance of x away. So our point is located a total distance of x plus h. So I have part of our ordered pair right now. Okay, I can go ahead and label that. From the origin, I move horizontally x plus h. Well, it stands to reason that vertically, I move f of x plus h. So now we have our ordered pair. Now I'm going to go ahead and connect those ordered pairs with a secant line. Okay, and I'm going to calculate the slope of that secant line. Okay, now when you compare the slope of the secant line to the tangent line, it doesn't even look close. But the magic is in the h. I had total control of the h. Look what happens if I make h smaller, that distance smaller. Okay? Look what happens to the secant line. And now that I have these 2 points labeled and connected with the secant line, I'd like to calculate the slope of this secant line. Okay, so let's go ahead and do that. All right, so we have rise over run. Okay, so we have change in y's, which would be f of x plus h minus f of x all over x plus h minus x. Okay, hopefully you can see that we have a positive x and a negative x on bottom. I'm going to cancel those. All right, so let me just go ahead and clean that up. All right, there we go. Okay, so we have the slope of the secant line. Now remember, I had total control over h. H can be as big as I want or as small as I want, as long as there's still 2 points. That's where limits come in. Okay, so right here, here's h. I have that control right there. I can make it as big or as small as I want. Okay, now remember, with limits, we can make h infinitely small. We can make it go to 0, but we can never make it actually 0. Okay? If I made it 0, then we would have the same problem. Instead of having 2 points, we would have 1 point. But I can make it infinitely small through limits. So let me go ahead and write this slope formula right here a little bit differently. I'm going to add a limit that makes h go to 0. Okay, so there we go. And that's the definition of a derivative. Okay, the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, now let's take a look at what happens when h goes to 0. Okay, and you can see that that secant line converges onto the tangent line. So because the points are infinitely close together, essentially we have the tangent line here. So the slope of a tangent line is defined to be this right here, which is a derivative. Hopefully I was able to help you understand the definition of derivative. Next, I'll be posting some videos on examples of how to apply this definition to various functions. So be sure to give those a look. Thank you for watching. See you next time.